pleasure and an honor for me to be here. I'm very happy to open up this series of lectures at IRENA. And I go back in energy, and I'll tell you a little bit why I feel particularly proud of this and honored by it. And that is, I go back in energy until times when you were not yet born, most of you. Early 70s, when the first oil price shock came, followed in the late 70s by the second oil price shock, and that put the world on notice that something needs to be done. So the United Nations then started to look at renewable energies, and there was a Nairobi plan of action that was adopted in 1981. And that started an interest in renewable energies that hadn't been there before. So the early IRENA days started with the preparations for the Rio conference in 1992, which was the first world conference on environment and development. There was one on just environment in 1972. And the Secretary General convened a United Nations Solar Energy Group for Environment and Development. That put out the report, which was a strategy in support of environment and development. And that study contained the proposal to form an international renewable energy agency. That went to the Rio conference, but was not picked up by member states. But I mention it because this was really taken forward by Hermann Scheer, member of the German parliament, who worked very hard for this to come about for many years. And my involvement in this was as chairman of the UNCEDED group that produced this report. So I have sort of some kind of feeling in particular for IRENA, which makes me very happy to be here. Now, going back to the situation, I will talk about the renewables, the socio-economic aspects of renewable energies and what can be done in such thing, what it means and why. And I think it's useful to take a look at the world as we have it and what is going on in the world in a slightly larger time perspective. These 12 graphs are all from 1750 to 2000. And this is, for example, population, GDP, foreign direct investments, damming of rivers, water use, fertilizer consumption, urban population, paper consumption, restaurants, transport vehicles, etc. And you see there's one common feature to all of these, and that is that it goes up quickly the last few decades. So we have a world in transformation that basically has happened during your lifetime, and it's going fast. And it's going so fast that there's now considerably concerns over a concept called planetary boundaries. Planetary boundaries being boundaries in one dimension or another that, if surpassed, would put the world as we know it in jeopardy. They come in different areas, like, for example, land system change. And land system change, you have a green area here which is sort of judged to be sort of probably okay, and you have sort of where we are, in this case in biodiversity, where you can see biodiversity loss is going way too fast for the world to be reasonably safe. Climate change is another one where the red extends way outside the green field. This is the nitrogen cycle, where it's also very red, while ocean acidification and stratospheric ozone depletion are areas of concern where the world is not yet, at least, outside the planetary boundaries. So this is the background. And then where does energy come into this? Well, if you look at this, obviously energy come into a number of things like biodiversity loss, land system changes, aerosol loadings of the atmosphere, climate change, ocean acidification, nitrogen in conjunction with biofuels, etc. So the way we look at energy in the context of planetary boundaries and Earth changes is very important. So what then do we need to do with the energy systems for the future? Well, obviously we need energy services, cooked food, transport, comfortable indoor climate, and so forth, called energy services. The illumination is the energy service. The electricity through which we get the illumination is an energy carrier. And this has to be provided for a growing world population. We expect another 2 billion people by 2050. And if economic growth continues more or less as is at historic rates, that's a 2% per year per capita on average worldwide. More in the developing world and less in the industrialized world. But we also need to provide access to the 3 billion or so people that don't have access to modern forms of energy, electricity and clean cooking fuels. So that's another enormous task to accomplish in the energy system. And as a matter of fact, if you look at it, you have 2 billion people here, plus 3 billion here, that need access over the next decades. That's 5 billion in total. The world now has 4 billion people that have access. So it's more than a doubling of the global energy system that is required for these reasons alone. Then, of course, this has to be affordable, and that is a question mark in itself. At the oil at $100 per barrel or more. And it's affordability at the household level, but also for corporations and for nations. There are many nations that currently spend more than their total foreign exchange earnings on buying oil, and that's obviously not sustainable. And to accomplish development under such circumstances is extremely difficult. Then, of course, it has to be reasonably secure supplies, and you have all the concerns about supply security that has been addressed to oil over the decades, but has also now become an important factor in the discussions over natural gas supplies. And there's a concern about energy supply security from the energy importing countries, and there is a concern about energy demand security from the energy exporting countries. And all of this has to be factored into the future energy systems. This is complicated by the peak debate. Peak oil is a common concept that you may have run into. And I'll come back to it. Peak oil referring to reserves not being sufficiently large and replenished sufficiently fast to meet a growing oil demand in the world. Then there's a number of regional health environment challenges like urban air pollution, like indoor air pollution, like acidification, and so forth. And that also has to be part of the equation. So as climate change mitigation, and I'll come back to that. And there are a number of ancillary risks related, for example, to nuclear weapons proliferation and relating to the linkages between bioenergy expansion and food prices. So here's a long list of things that require change of the world and the local energy systems if we are to see something like sustainable development and a sustainable future. So the way energy systems are to be designed has to do this, and it will require major energy system changes. So this is an indication of the situation and the challenges facing us with respect to energy. And you have to realize that these challenges must be adequately addressed, timely, and simultaneously. We can't take one or two at the expense of others, because then we just end up in a different misery. So this is now what needs to be done. So how can this possibly happen? Looking back in the energy history from 1850 to the present, you can see how the global primary energy has been growing from 1950 much faster than before. In the early days, 1800s, this was almost entirely biomass used for all kinds of purposes. Coal came in towards around the turn of the century, followed by oil, natural gas, nuclear and hydro, and a little bit that you will not be able to see of new renewable energies on the top of this. So this is the world energy situation and how it has evolved. Now, if we look then at the climate issue, then we need to remember that the climate issue is linked here in the sense that approximately 2/3 of the greenhouse gases that are emitted globally originate in the energy systems, mainly through the use of coal and oil and some natural gas. So if climate is a concern, the use of fossil fuel, the way it is being done at present, is also a big concern. The IPCC, Intergovernmental Panel on Climate Change, in its third report, came out with these red embers. The red embers have a temperature scale here from the pre-industrial temperature, that is the 1800s, to the around 2000 temperature, which was 0.6 degrees higher. And then the temperature goes up, future projections of world temperature, global mean temperature. Here are 5 different areas of concern. So this is risks to unique and threatened systems, risks to extreme weather events, distribution of impacts, aggregate impacts, and risks of large-scale discontinuities, like the Greenland ice melting, raising ocean sea levels significantly. That will be such an impact. Now then you look at the colors as you go up. So the judgment in year 2000 was that, well, this is probably more or less okay, but if we go up by a degree or two, we move into a red, more dangerous zone. And similarly for the other areas of concern here, large-scale discontinuities was considered like can probably have another 3 degrees warming before running into serious difficulty. This was the judgment 10 years ago. This is the judgment updated with what the world learned in the first decade of this century. You have the same bars, same people did this, and what you can see, or what you could have seen, is the red fields here moving down by a little more than a degree or so. So what we have learned over the last 10 years is that the situation is more serious than it was thought to be 10 years ago. And this goes for all of these dimensions. This is the +2 degree line that everyone talks about and that climate policy tries to stay below. +2 degree warming above pre-industrial level here. And as you can see, 10 years ago, that looked a little bit questionable, but could perhaps live with it. If you look at the situation now, 2 degrees is quite a lot in most dimensions. Even large-scale discontinuities are brought into the discussion. Consider then that the world is now heading for 3 or more degrees global warming. The path on which we all are is far from encouraging. And this is where a lot of people think one should aim at, that is staying below 1.5 degree warming, out of which we've now we've seen 0.9 degrees. So it's really getting very, very close. Now, what would it then take to stay below 2 degrees? The estimates that have been made are that global emissions to stay below 2 degrees with a 67% probability, which is not very high. You know Russian roulette, do you? You have a revolver, you put in 1 bullet, then you have sort of 80+% probability to survive, and you wouldn't play it. This we're playing with 67% probability. But to do that, the emissions that have gone from year 2000 to the present to here, and this is projection out to 2050, this is sort of one, we peak now and go down moderately. This is a reduction rate here of almost 4% per year. But if we don't manage to reduce emissions until 10 years from now, we would then have to reduce them here by something like 9% per year to stay within this criteria. That is effectively saying it will not happen. So it illustrates sort of the magnitude of the dilemma we are all in. This is the way we're heading. We're not heading downwards in emissions. We're heading upwards, and significantly so. This is the IEA sort of standard reference scenario saying what will happen if the world continues with the current policies governments have put in place. And as you can see from here on, this is coal, this is oil, this is gas, nuclear and hydro, and biomass. And up here is a little wedge of renewables. This clearly is in violation of all of the sustainability dimensions that I indicated to you. But this is where we're heading. And I come back to the peak oil. Could this happen? As governments now seem to believe and are in effect allowing to happen. This is the peak oil situation. These are a billion barrels per year. These are the blue ones are the discoveries. And as you can see, from 1930 to the present, most discoveries happened before 1980. That is here. Production have been continuously increasing. Here we had a dip because of the oil price situation, and now production is continuing upwards. And as you can see, for the last 30 years, production has been much larger than the rate of discoveries. So we are depleting the known reserves. And we're also depleting the areas where people are looking and hoping to find more oil. So even if you manage to take a new oil field in operation here later this year, as announced in the newspaper today, that will not change the overall situation. We have a production which is very large. This is about 30 billion barrels per year. So the question is, are we running out of oil? Well, not physically, because there will always be more in the ground. It just will be more expensive. So what is likely to happen is that pressure changes to make liquid fuels from coal and other heavy fossil fuels, which is technically possible, but environmentally very difficult. And it's costly in addition. And it brings more carbon dioxide rather than less. So this whole situation translates into a need for energy systems transformation, and a major one, where the main elements are energy end-use efficiency and renewable energies. And this is where the rest of what I will say will be more or less focused on the renewables. There's carbon capture and storage, which is discussed sort of in conjunction with power plants fueled by coal, etc. And this would of course be very good for climate change mitigation, while using end-use efficiency and renewables, when you go through the list, turns out to be good for all from the point of view of all of the concerns that the world is facing in relation to energy. And that's why these are the most important and interesting areas to look at. I will give you one example on energy and use efficiency before I start on the renewables. And yes, efficiency and renewables, we don't want them because that we like them. We want them because they can be seen as instruments to achieve sustainable development in all the dimensions I indicated. The efficiency example I'll give you is the passive housing. Passive housing is interesting because about 30% of world energy is used for indoor climate, cooling in the warm areas and heating in the cooled areas. Passive housing refers to using technology that brings down this energy need by 90%. We now know we can construct and operate buildings using only 10% of the energy that was regularly done and is mostly done still today. So if this technology was employed, that would have an enormous impact on the demand for energy in the future. And the interesting thing is that this can be done, and here are a number of pictures of examples. There are tens of thousands of these houses that have been built, mostly in Germany, Austria, and Switzerland. They are typically about as expensive as regular houses. Yes, you have to pay more for better windows, better insulation, but you don't need a heating system. So you shift the investment, basically, and the operating cost, of course, will go down very much. The interesting thing is you can do the same thing in reconstruction. And every 50 years or so, say an apartment building needs a major reconstruction because it's just wear and tear. You need a new facade, you need new windows, etc., etc. And if that is done with energy included as an important parameter, you have the same 90% possibility. And well, these are pictures of before and after buildings. So there's a major opportunity here. So if you look at floor area in a projection from 05 to 50, this is a projected floor area expansion. This is the stock in 05, which will be dwindling. Some will be torn down, some will be retrofitted in standard retrofits and in more advanced retrofits. Then you will have new buildings, these ones, standard new buildings, and the advanced new buildings, the passive houses. So with this floor area going up 126%, you have a thermal need situation that goes down by 43%. And these arrows have been misplaced for some reason. But it means that this technology has the potential, if used, to really change the situation in the buildings area. If you look at transport, electric transport operated by renewable electricity has the same or similar potential. If you look at industry, there are many opportunities as well. Let's then go to renewables. Looking at the share of renewables in global final energy consumption 2009. Fossil fuels were 81%, renewables were 16%, and nuclear just below 3%. So these are the main components. And in the fossil category, oil was the largest, followed by coal and natural gas. If you look at renewables, 10% out of the 16 was traditional biomass. That is, biomass used in the rural areas, mostly for cooking and some heating, leading to rather large problems with indoor air pollution and with outdoor air pollution. So it's a major problem for women and children that get exposed to serious concentrations of these pollutants. But it's also a major problem from a climate point of view, because the poor combustion conditions for this biomass lead to emissions of unburnt hydrocarbons like methane that are strong greenhouse gases. Hydropower is a little over 3%. Biomass, solar, geothermal for heating, 1.5%, biofuels, 0.6%, wind, solar, and other electric technologies, 0.7%. So that's a very low contribution to the final energy consumption in 2009. So that's where we are on that overall situation. If we look on the renewable share of electricity production, 2010, fossil fuels had a slightly lower fraction, 68%, hydro 16%, nuclear 13%, and other renewables, non-hydro renewables, 3.3%. This is very hard to read, but it shows a time scale, which I think is from 1972 to 2008. And this is how the evolution has been of hydropower and of primary solid biomass. It's rather slow but increasing development. This is you can read better than I. This is MSW, municipal solid waste, followed by solar thermal, followed by geothermal, followed by wind energy, and you can see the borderline is about there. And the last one here is biofuels. So this sees an expansion that has been significantly there for the last 10 years or so. These are the very rapidly growing ones. This is solar PV and ocean. Ocean is down, but the big one here is solar PV, and I'll come back to that. So you see that there's recent activity here that is quite considerable. So if you look then at the renewable power capacity around the world, when it comes to non-hydro renewables for electricity, in the world there's about 300 gigawatts. That is 300,000 megawatts. The big one at the bottom is wind power, biomass power, solar PV, geothermal, and a little bit of others at the top. But what you can also see is that quite a dominating part of this 300 gigawatts occur in relatively few countries. Developing countries as a whole are not seeing too much of this happening, but there is some. The European Union has quite a bit, but then the United States is not that much. China is growing very rapidly, Germany, Spain, India, which means that in most countries not very much is actually happening. But there are some where a lot is happening. And if you look at the different technologies and their growth rates, this is the growth rate in year 2010, that is over 2009. And this lower one is the 5-year period, 2005 to 2010. So if you look at solar PV, in total that's grew 72% last year and has been growing by 50% on average for the last 5 years. Quite impressive growth rates. If you look at grid-connected solar PV, it's even more impressive, 81 and 60. Wind, 25. Concentrated solar thermal, I'll come back to that, 25% over the 5 years, but 77% last year. And then those that don't move very fast, geothermal, hydro, solar water heating, 16% is very respectable in all other areas. Here it's relatively constant and not at the top. Ethanol production has actually been going down because all of the voiced concerns and the opposition from the oil industry, not to hide the most important factor. Biodiesel, also the same on the 5-year period, relatively high, but slowing down quite a bit for the same reason. Now, how long could this possibly go on? How much more renewables could we tap out of the systems? And this is one of my favorite figures. It shows incoming radiation from the sun up here, how this energy passes through numerous systems on Earth and returns to space as long-wave heat radiation. And of course, what goes in, some is reflected and the rest goes out here. Now if you look at the quantities that go out here, 4 million exajoules. 4 million exajoules, and the world is now using 500 exajoules a year. So that's a factor of 7,000, 8,000 or so more than all of the energy use that humans enjoy at present. So the question becomes, could we reroute some of these energy flows to tap into them and get the benefits of energy use that we are looking for? So that's really the big question. And as you look at what is going on here, this is the hydrological cycle, this is the weather system, this is the direct radiation, this is not the least biomass, the photosynthesis. Photosynthesis is about 8 times larger than total human energy use per year. And down here is also a small contribution of geothermal that can be used. That is not coming from the sun, it's coming from sort of stored heat deep inside Earth and decay of radioactive products that were formed at the time of the formation of the elements and are still decaying and releasing heat. So unquestionably, the flows are sufficiently large for all people, for all times. The question is just, can we have an intelligent way of actually tapping into them so that we get the benefits we're looking for? So if you look at the range of technical potential, that is bringing in lots of constraints. This is based on what we now know as technologies. We have some for electricity, some for heat, and some primary energy, that is, in this case, biomass and direct solar that can contribute both heat and electricity. This is electricity demand at present. So the potential from geothermal alone is much larger. And note that this is a logarithmic scale. So it's 1, 10, 100, 1,000, 10,000. Geothermal alone could produce all electricity. If you look at ocean, that's much more uncertain. Wind energy certainly could produce much more than global electricity need. Geothermal is probably not sufficient alone to deal with the global heat demand, which is this level. And if you look at global primary energy, biomass would probably not be sufficient at present with present technologies, but direct solar is at least one order of magnitude larger. So, no concerns on the technical potential. Look then at what is happening with wind energy. From 1996 to last year, global installed capacity has been growing, and the last several years has been growing quite significantly, almost 40 gigawatts this last year in increase. And so the installed capacity has increased, but the size of the machines have also increased. If you go back 10 years, a typical size was about 1 megawatt. Now it's about 3 or 4 megawatts. So sizes are expanding quite a bit. But also here, it's not in so many countries. This is the installed capacity end of 2010. So for China, it was 44, 45 gigawatts. And as you can see, there is a change in color here. This is what they did in 2010. This is what they did in all the years before 2010. So if you look back in China, it turns out that China has doubled the installed wind capacity every year for the last 5-6 years. They didn't quite double it last year, just almost. The US, I think the borderline is here, is number 2nd in the world. Germany, 3, Spain, India, Italy, France, UK, Canada, Denmark. And where's all the rest? Nowhere present. Look at solar PV in the same fashion. It got started slower, but later, but as you can see, the last few years, enormous expansions, and I indicated the average growth rate earlier, so you saw those numbers. So what is happening then with costs? Costs are here displayed as a function of cumulative global capacity. That is, what you can see is how the price in US dollars per watt on a logarithmic scale, 1, 10, 100, has been going down for PVs, silicon PVs, and it's going down from the 1970s as investments in increasing capacity has offered learning opportunities of all kinds. It went down, it became more slowly, and here you have even a little bit of a price increase because there was a shortage of silicon, and then it dropped again, so now it's down here to a little over 1.4 US dollars per watt last year. So that's a pretty dramatic development. And this has to do with the fact that this is modular, small-scale technology. You can learn how to do it. and that is what the industry is doing. The wind, this is onshore wind in Denmark or offshore wind in the US. They have a similar development, but they have been going up a little bit here. This has to do with increased costs of various kinds. There are land use problems, there are siting problems, there are all kinds of difficulties. So we will see where that goes. This is, however, the most interesting PV cost development. This is a different technology. First Solar are making cadmium tellurium photovoltaics using a different technology than the standard silicon technology. And as they do that, in 2004 they were at almost $3 per watt. In 2009 they were just below $1 per watt. The last I've heard is that they're now at 0.8, and they're continuing down through various activities, and they aim at being just around $0.5, $0.6 per watt in 2014. That's a remarkable development, and it's actually moving solar PV technology into an area that people have been dreaming of. $1 per watt was the target for a long time, and now we're there, or even further. So if you look at what that means to achieve grid parity for solar PV, grid parity is comparing the cost per kilowatt hour with the grid. This is sort of base load utility power. It's down here at a few, like 4 or 5 euro cents per kilowatt hour. This is the peak power. It's much more expensive to generate power when demand is high, for example, for air conditioning in warm countries. And here we are with PV costs coming down. If you have a sunny area, this is 1,800 hours of sun per year, and you are sort of getting into the area of conventional peak power. The projections here are that by 2020 peak power will be fully competitive, and if you go out another 10 or 20 years, you're down into the bulk range of conventional electricity as we do it today, and assuming that those costs will not go up. So it's moving there. This you can't see, but it represents solar towers. There's a tower here, the mirrors, they reflect the solar energy up on the top of the tower. It boils water, generates steam that is sent to the ground and operates a turbine, and you get electricity. And here's another configuration that we also cannot see. Now, what then are the costs of this and at present? And this is our cost from demonstrated technologies. Here you have some electricity, biomass electricity, solar, geothermal, hydro, ocean, and wind. Now for each one of those, there's a median value, which is sort of an area with a lower bound and an upper bound. So here's the lower bound, and the upper bound is way up here. So the medium is this one. How that compares to this is the range of non-renewable electricity costs is about here. So you can see that wind energy in good areas are pretty competitive. Hydropower definitely, ocean definitely not. Same situation here for heat. This is the range of conventional systems, biomass, solar thermal, and geothermal heat. It's getting quite competitive. Biofuels compared to gasoline and diesel, in some areas quite competitive, in others not, and I'll come back to that a little. So on the whole, renewable technologies are not quite there to do it on their own. The investments that have taken place are largely due to the fact that there are government support programs that are quite significant. Then we have this problem of intermittency. That is, if you have a coal-fired power station, you know you can turn it on and off and up and down as you need to meet variations in electricity demand. But if you look at wind power, you have it when the wind is on, you have the solar when the sun is out, and it varies over the days and over the weeks and over the year. So that, of course, leads you to have to think in different terms on how you operate a power system. So there was a renewable combi plant. This is an experiment that has been done in Germany to show if you can really have 100% renewable electricity and still make the system work. So they think in terms of solar contributions, wind contributions, biogas, excuse me, biogas, which can of course be stored and used as needed for transport fuel or for electricity generation. You can have reservoirs like water in dams that you tap as needed, but you can also put energy into compressed air energy storage. So when you have excess renewable electricity, you push it into a big cavern, and when you need more electricity than you get from the variable sources, you release that compressed air through a turbine. And you deal with the demand. Some demand of electricity you can change in time. Like, for example, there's a lot of talk about changing some things like laundry and drying operations to the off-peak hours during the night. And many families are starting to put laundry and dishwashers at work overnight rather than in the daytime for such reasons. And that's getting into what is called smart grid operation. You try to apply a systems approach to look at the combination of demand and supply and make it work together. And this is what is being done here. And it's an exchange with solar energy coming in on the forecasts about what will the production be, so that the central unit knows how to run these systems. Likewise for wind, forecast and the production. So this was done for the year 2006. And it turns out that this is the average by month and how it worked. And you have the wind, PV, biogas, hydro, and imports. And a little bit of imports in some months. So it was basically a proof of concept. Yes, we can conceive of these systems dealing with the intermittency, but it requires a new thinking. It doesn't work if you use the sort of regular power system engineering thinking, because there's not enough flexibility for that. It's interesting to look at sort of these energy flows. These are solar resources in the Middle East, North Africa region. So this is this central towers I talked about before. Here's a parabolic trough with a parabol reflecting radiation to a central tube where steam is generated. If you cover an area the size of the Aswan Dam, that could harvest energy equivalent to the annual oil production in the Middle East. So that tells you something, such a small area, and that could produce the same quantity of energy as the Middle East oil production. Just tells you something about the enormous flows that are around. And that means that if you look at the area of Sahara, this is area used for all agriculture in the world. Sahara, if you set aside a little square, I hope you can see up here, that's enough to produce all European electricity. This is enough this area would be enough to produce all global electricity. So just to again come back to the large flows. And there is technology to move the electricity, like high voltage direct current transmission lines. And it opens the possibility that you move electricity from from the deserts to load centers, or from the windy areas to load centers over long distances. The Midwest of the United States has the wind belt, which has enough electricity potential in wind to produce 4 times the US electricity consumption. And with this HVDC technology, you can move it to the load centers on either coast. So it opens up for totally new ways of thinking and acting in this area. And it's an integration. It's not that you have all small scale or all large scale. You have a combination in this kind of a system. Here, for example, you have the central station power from solar feeding into HVDC and coming into various levels of the distribution and systems. Wind energy would feed into also smaller grids, and the photovoltaics would feed into the 200 to 400 volts systems. And when it comes to the larger systems, this is a vision of Europe using HVDC lines and having solar production in the southern Mediterranean areas, having wind in the northwest of Europe, hydro up in the north, geothermal in different places, and bioenergy also some areas in the middle and central Europe. So that's how to think about these, how they link together and how they could work together. Coming then to biomass. This is a schematic over various paths to liquid fuels, from fossil fuels, from biomass. Second generation technologies and the first generation, that the one we see now. And as you can see, I'm sorry, excuse me. There are many ways through which one could go to actually produce the fuels that are desired. Like, for example, green diesel, biodiesel, ethanol, butanol, mixed alcohols, DME or Fischer-Tropsch liquids. That can be used for regular gasoline or diesel. So what we're seeing here is that there are some of these that work at present. Those that a lot of hope is attached to, lignocellulosic biomass. There are various ways to go through that and arrive at ethanol. This is what is hoped for, because it would take pressure off land use for the biofuels we see used at present, particularly in relation to palm oil for biodiesel and in relation to ethanol production from sugarcane in many areas outside of Brazil and some other countries where land is abundant. This is production cost for biomass to power and CHP, and there's a long range of technologies here, and you can see the cost here in US cents per kilowatt hour sometimes are down quite competitive, and this is direct co-firing in coal plants. So you co-fire bioenergy with coal, and the cost for this becomes quite competitive. And co-firing bioenergy with coal is very interesting also if you combine it with carbon capture and storage. Because in effect, you then you take carbon out of the atmosphere in photosynthesis, you have the biomass, you put that into co-firing, you take the carbon and you put it back in the ground. So in effect, that is taking carbon out of the atmosphere and putting it into the ground. This is a very interesting way of looking at it. But as you can see, also other power technologies are in cost ranges that are not far from what is being done otherwise. This is the selling price of ethanol, the upper curve, as compared to the Rotterdam price for gasoline. This starts back in the 1970s and it goes to the present. And about 2004, the gasoline price went above the ethanol price. And this is price per gigajoule. So here we're already there. Half of the automotive fuel in Brazil is ethanol. And it's quite a good business for the country. It's local jobs, it's cleaner, it's no imports, and the costs are lower. And projections for gasoline and diesel costs as a function of the crude oil price on the world market. This is ethanol from lignin cellulose. Sugarcane is lower, as we saw. And these are projected costs for 2030. And for biodiesel, we're here. So if you look at sort of mid-range here, this corresponds to an oil price of about 110, which is where we are. So this is not far off. And if you move down to the projected cost, then that corresponds to oil cost of $70, $80 per barrel. So this is within reach, even under standard economic evaluation terms. Now, some people say, well, you have to put in more energy to get that bioenergy or other renewable energy out of the system. How is it? If you take first generation biofuels, this is sort of, you put in as much energy as you get out. That is, you don't gain anything. If you look at sugar cane Brazil, it uses a few percent of the energy that is then generated in the form of ethanol. But if you look at US corn-based ethanol, it could be a very negative operation on an energy balance point of view. So it varies. These are greenhouse gas emissions exclusive of land use issues for electricity generation. And if you look here, they're generally quite low compared to natural gas, oil, and coal. And if you put the CCS on the coal use, you come down to this area, and natural gas and CCS to this range, and you're still above what you can achieve with the renewables. So CCS helps, but it doesn't help as much as renewables. And then this is the area, the types of technologies I talked about, biopower with CCS, bringing you negative emissions, everything considered. This is where you have the geothermal capacity in the world. Most of it comes in this part of the world, but there's also significant contributions in Kenya, and the United States uses quite a bit as well. Italy in Europe is the largest in Europe. So if you look at the renewable power capacity addition as a percent of global power capacity additions, in all investments in renewable power. In 2004, that was about 10%. In 2009, it was 36%. So this again illustrates the enormous expansion that is taking place. It doesn't affect the generating capacity in total, fraction of the total existing generating capacity, because it's still starting from a low level. So some overall observations of renewables. It's decentralized and centralized. It's small scale and modular, which opens the way for rapid expansion and also for learning. There are quite a variability in conditions, what you can do where and how you do it. It has to be an integration with energy demand. And you have to build systems that handle the intermittency, the base load concept, as power system engineers like to think of or liked to think in, is no longer applicable for these new systems. We need smart grids, as they're generally called. How are we doing for time? This is 11 o'clock now, is it? Renewable energy and sustainable development. So if you do if you use renewables, you can contribute in many dimensions to social and economic development. Cost savings, particularly in remote areas, but also coming into more general areas like the ethanol case, for example. Reduced energy imports, which for many countries is a very high priority for the reasons I mentioned. Domestic jobs is always a concern. It has been one of the drivers behind the large interest in Germany to capture or build an industry in this respect. Renewables can also help accelerate access in the developing countries where lots of people don't have access to electricity and clean cooking. And this is 2.7 billion people. Contribute to more secure supply of energy, reduced greenhouse gas emissions, improved health due to less pollution. So looking at the history for the last 15 years, investments in new grid connections per year, you see the wind coming back, the very large expansion we have had, the solar photovoltaic, this is 2010, and you can see nuclear, which is often talked about, has been hovering around 5 gigawatts, was down to 0, and it's now up a little bit again, and is much talked about, but doesn't play as large a role as you could sometimes believe. And that has to do with the fact that we have negative learning when it comes to costs of nuclear. These are investments in the US and in France, and this is dollar per kilowatts as a function of cumulative investments in gigawatts. And as you can see, they were quite low here, $1,000, $1,500 per kilowatt. But it started to go up in the 80s. The reason it started to go up in the 80s has to do with the accident at 3 Mile Island, which was the first serious reactor accident that occurred in 1979, I believe. And then costs have been increasing and has been going up quite dramatically, and is now up around 5,000. If you look at the 2 reactors under construction by French companies, one in France and one in Finland, they are up here. And it's interesting to see that they have all followed each other's different types of reactors, but the system here goes the same way. And what the impact of Fukushima will be on nuclear construction cost remains to be seen. I would suggest then we take a break. I think my throat needs a little bit of relaxation, so if that's okay with you, let's try to be back in 7 minutes sharp. This was sort of to go over a number of the issues the world is facing and how energy has a role in it. I also went through what the renewables could do in this respect, and sort of the socio-economic aspects that are involved and underlying all of those things that I went through and covered here. Now there remains an important set of issues, and that is to say, can we build energy systems over the next 40 years or so until the middle of the century that actually addresses all of these concerns at the same time, quantitatively? And this we looked into in the Global Energy Assessment. So we did a backcasting exercise for 2050. Backcasting means you define a state and you see if you can bring yourself there. And so that was the question. The state is that energy systems need to support economic growth at recent historic rates, provide universal access to electricity and cleaner cooking by 2030, reduce air pollution, urban and indoors according to World Health Organization guidelines, avoid dangerous climate change, that is stay below 2 degrees above pre-industrial. If that is to avoid dangerous climate change, it seems to be a relatively open question. I would, in my judgment, it is not sufficient to stay below 2 degrees. Improve energy security, and in the process address peak oil and nuclear proliferation challenges. So can we do all of that was the question. So the analysis starts with this branching point where we are, and it goes into, starts on energy efficiency being differently. One very energy efficient future, one not so efficient, more supply oriented, and one intermediate. In each one of these three main branching points, we look into various forms of organizing supply to meet the resulting demand. And as we can see, we looked at a large number of different combinations. If we have high energy efficiency systems, we have lots of flexibility on the supply side. If we have low energy efficiency, we still can do it, but we have less flexibility on the supply side. So in this example with the efficiency case, this is where we are at present, so this is how it would evolve until 2050, which is more biomass, less coal, less oil, less, or all, not much, but a little less gas, no nuclear, and renewables coming in and doing this part in this particular case. In all other cases we looked at, this is the efficiency, the mix, and the supply cases. And these bars here illustrate various sensitivity analysis or sensitivity combination that were tested. Like, for example, the various, this is a case with no CCS. This is a case of no nuclear. And if you have high energy demand, there wasn't a combination possible that met all the criteria, while in these others they were. And it turns out that, as you can see, of the 60 different combinations that were tested, 41 actually works. So it means that the major finding here is that there are many opportunities to make this work. And in fact, it also translates to say that the world could do better on various issues. That is, for example, support higher economic growth, reduce emissions more, enhance security more, by doing more along these different lines. If you look at the renewables, which is the part up here, it varies in the efficiency case, and it typically stays around 30 or 40% of all energy by 2050. So it's a very modest contribution in relation to those that have looked into 100% renewable systems for 2050 and found that that can conceivably work. We have not taken it that far here, but it's clearly a very interesting case. And even if we go for the high supply case, there is a combination that can do this, and this particular one, we looked at sort of the possibility of doing high supply without nuclear. And the nuclear case here is one of these green wedges that is basically phased out by 2050. So it can be done. There are lots of flexibility in the system. This one I think we skip. Now, if we look back at the major expansion that we've seen, particularly over the last 5 years in wind and photovoltaics and other renewables, they largely go back to various policies and programs that have been put in place. And the reasons are, of course, that there are these benefits, the socio-economic benefits that come out of renewables are sufficient to justify that governments actually make an effort to produce conditions that are such that investments take place. And this has to do with the fact that the general policies and institutions that exist in the energy area favor the incumbent industry. I'll come back to some examples how this works and why it's important to address it. Incumbent industry being the fossil fuel industry, the nuclear industry, the large-scale electricity industry. There are lots of market failures. For example, the fact that social benefits and social costs and benefits and environmental costs and benefits are not reflected in the market conditions of investors. So what the world is basically doing is, hey, we have all these concerns and we know that renewables can help, but those that are going to invest in nuclear, they cannot look at any benefits for themselves coming from these social and environmental concerns. They have to do it on economic evaluation only to a large degree, and therefore much less investment would follow. So some governments have realized that, put into place various mechanisms, and what follows is that we've seen in some countries quite considerable investments following. And of course, there's a serious lack of education and access to data, and that goes basically in all countries, even where you have a lot of investments taking place, because this information is not easily available. It's regularly not part of education. If you look at, for example, the example I gave on passive houses, architects and construction engineers don't learn about these things. That's not what the teaching in their education contains. And how then can you expect them to do it? So there's a serious issue of building renewables and efficiency knowledge into the curricula in education at all levels and professionally, and particularly for the professional groups that have to be central to any advancements in this area. Now, generally speaking, this is summarizes sort of the development path from product development to market expansion, and roles of governments along the way, roles of business and finance community along the way. And it starts with sort of basic R&D and costs per unit that can be expected to come down, and you have an R&D applied demonstration phase, and you have no market expansion to mention. It only comes later. And you move from the basic R&D phase to the applied R&D phase to demonstration to pre-commercial to niche markets and supported commercial to fully commercial. And to bridge over here, this is called the valley of death. A lot of technologies make it this far, but they never make it into this region. So the valley of death is what needs to be bridged. And the bridging mechanisms are market engagements programs, strategic deployment policies, and barrier removals. So this is a sort of a technology push, and here is a market pull effect. And both of them are influenced by the policies and programs, by governments in the first place, but also by the financial and business communities. Here is one of the interesting cases of government policies. These are global energy subsidies as they exist. These numbers are from 2009. And the global subsidies here are sort of the order of $500 billion per year. $500 billion per year subsidize energy. This little wedge here is the non-fossil subsidies. That is by far subsidies from governments to the energy systems goes into supporting fossil fuels and nuclear. And if the objective is sustainable development, one can wonder why so little goes to the areas that have the highest promise. Look at another interesting government policy. This is public sector energy R&D in International Energy Agency countries by major technology group. IEA is about the same as OECD. These are R&D investments from 1974 to almost the present. I talked about the oil crises of the 70s, and this resulted in drastically expanded energy R&D, which peaked in the early 80s and then tapered off to a minimum around the turn of the century and a slow path back up again. As a fraction of government total R&D spending, energy R&D is declining and has continued to decline since the early 80s. Now, and that's also interesting to see, why is it so low and in relative terms declining when this is such a central area of action to bring each and every country on a sustainable development path? Now, where is the money going? This is nuclear without fusion, and this is fusion. You know, nuclear is fission. You separate, you divide uranium atoms and you get energy released. Fusion is you put hydrogen together to helium and energy is released. Fusion has been sort of the dream of the nuclear engineers since the idea came about in the early 50s. And it pulled me into becoming a nuclear physicist, fusion and the dreams of fission. And fusion at that time was 40 years distant until we would have solved the fusion problem. That was 50 years ago. We still hear from the fusion people that it takes only 40 more years. So, so much for that. Then you have fossil fuels. You have the renewables are in here, and you have this is efficiency. So if you look at the relatively constant distribution of the R&D money, you can see that there's not much variation, and efficiency has received a little more than 10%, more or less constantly. Renewables is around 10% over this time period. And again, one wonders, if analysis shows that you really need to go efficiency renewable direction to accomplish significant changes needed, money is not going in that direction. Here is an analysis of the past and current R&D into these technologies, efficiency, other fossil fuels, renewables, and this big chunk here is nuclear, with including fusion. Now this is where the analysis we did in the global energy assessment showed R&D money needed to go, and in some average case this would be efficiency. You would have the nuclear up here dealing with waste and other things, and the renewables would have a large chunk as well. So this is another area where government policies are inadequate. Now, some examples of policies that would be required. Feed-in tariffs is a very interesting phenomenon to make money go into realizing renewables and therefore realizing the potential it has. The tariff means that investors know under such a system that they will get paid at a certain rate per delivered kilowatt hour for a certain period of time. So they know they have access to the grid, so they can sell the product, they know what they get paid. It's quite a limited risk in comparison to many other things investors can do. And if you set these rates sufficiently high so people make money, investments follow. Germany is the prime example that has demonstrated this together with Spain. And now it's coming in other countries as well. Quotas is another system that is used, for example, in my country. The system needs to have this much renewables, and you can make that work. But the trick is that you never can get an agreement to have the quota so high that it really matters. And it's a nice way of keeping a lid on renewables. We're very positive to renewables, but let's not have too much of them. Then you get a quota system. If you really want them, you make a feed-in system. Grid access is a very high priority thing. If you cannot access the grid under some kind of secure rule and get compensated for what you produce, you will not see any investments. Build renewables into the construction sector together with efficiency. Biofuel blending requirements. We have in Europe a blending requirement, I think it's 10% by 2020, and that drives development of the industry. But it's again one of those things where it's not open-ended. If you satisfy that agreed number, then you get that and no more. Bioenergy sustainability criteria are extremely important, not to forget, because bioenergy can be a very good contribution, but it can also be dangerous for biodiversity, for example. These are sort of specific examples. If you take some more general ones, the design of loans, guarantees, and grant programs to drive investments. There's a land use planning requirement, particularly for transmission lines and for bioenergy. General fiscal and tax policies. Carbon taxes, carbon pricing is quite important. Sweden introduced a carbon tax early 90s, and it's now about 100 euros per ton, quite high by all international debate. But it has driven a change from coal to bioenergy for most of the heating in Sweden, which means we have reduced greenhouse gas emissions from 1990 by 12, 13, 14%. At the same time, the economy has grown by 60%. And the trick was a carbon tax that put bioenergy in place and therefore captured a lot of the socio-economic benefits inherent in going for renewables. I said that feed-in tariffs are effective. This is wind power investment in the EU. In countries with feed-in tariffs and in countries with quota systems. And as you can see, it's quite clear what works and what doesn't work, as I indicated before. These are the EU renewable energy targets, and they basically say that the 20% renewable energy target for the EU for 2020 is distributed among countries. Some countries have very little renewable energy and will not expand to 20%, but something much less. While some countries, like Sweden, I think is on the top, we have a target of 49%, and we are in fact already at 48%. So it's not very ambitious. But it varies, and efforts are being made. Now, if we want to deliver on all these parameters, it's not just to bring energy technology, it's to have urban planning that brings in efficiency, brings in renewables, brings in new transportation system. Material use is a very important area, as materials production uses 2/3 of industrial energy use. And this is one of the reasons why metal recycling is so important in an overall sense. Land use I touched upon. Consumption patterns are of course very important. And the world is fooling itself at present. For example, I said Sweden has reduced carbon emissions by 12%, which is true. But a lot of the manufacturing of products we use in Sweden has moved to China. So the emissions take place there. So if you include those emissions in the Swedish picture, it's not -12, it's +20 or something like it. And this goes for the whole of the Western world. Consumption patterns, the most important part of consumption is probably the diets and the fraction of meat in diets. From a carbon point of view, FAO found 2 years ago that 18% of all greenhouse gases emitted in the world come from the production of meat. It could be compared with the transport sector, all automobiles, etc. That represent 14%. So the quantity of meat, particularly beef, that goes into the diet is a very important part of the consumption pattern that plays a role here. What also plays a big role is tourism. And it's very popular in Scandinavia to have tourist trips to Thailand and other distant warm places. I can understand that people like to go to warm places, particularly in the winter, but it has a considerable impact on energy and greenhouse gas budgets. Now, coming back to why one should look at the renewables and all the benefits in the renewables. The multiple benefits concept, I think, is central to this. Multiple benefits refers to getting benefits not only in terms of an energy carrier like electricity delivered to the grid, but also getting the benefits in terms of jobs creation, in terms of economic growth, in terms of security, different kinds, in terms of health, local environment, and so forth. All of those benefits derive, socio-economic benefits derive from the use of renewables. And this is why it's so interesting to use them. And this is why the push for renewables needs to be there. But it means that if you say we do renewables because of greenhouse gas emissions, and climate change people often reason that way, and then they say there is a price, a cost in terms of per ton of carbon avoided. And you can hear people talk about the carbon price, the value of the carbon avoided, and that being translated into part of the price the consumer would have to pay. And that is, of course, correct. It should be like that. But that is only to account for one of the many areas that are affected by the investment, because you have these benefits as well. And why wouldn't they be reflected in the market price? The net effect of that is that when someone says that, well, it costs too much in dollars or euros per ton of carbon avoided, that's a totally misleading statement, because it doesn't include all of the benefits and all of the costs that are actually there. And this is a major market failure and systems failure, which is behind the fact that, relatively speaking, so little happened in the renewables area. Energy efficiency and renewables, of course, deliver all multiple benefits and are therefore very attractive. But what is perhaps even more important in this respect is that efficiency in renewables can be justified on local and immediate grounds, rather than on grounds that are global and in the future. So that means that, for example, if you look at China, China is not very famous for avoiding carbon emissions. They are increasing the most in the world. But they're also famous, as a little bit indicated, for pushing renewables harder than anyone else in the world. And efficiency also pushed harder than anywhere else in the world. And China is doing this because it's good for China. It's local and it's immediate. It comes in terms of avoided further expansion of coal mining, urban air pollution, local pollution in general, acidification, and other immediate concerns that China is preoccupied with. So there are reasons to do the right things from a climate point of view for other reasons than climate. And it has led me to believe that the climate negotiations are stalled because they only deal with climate. They don't deal with the entire situation. And it's not possible to go and sell investments in efficiency and renewables on climate grounds, because as we saw at the Copenhagen climate meeting almost 2 years ago, the whole developing world said, well, climate is a concern, but poverty alleviation and economic growth for us is a much larger concern. And who can argue against that? The only argument you really have is to say, well, if you want to grow your economy and have poverty alleviation in a sort of sustainable way, go efficiency renewables. Then you happen to address the climate problem as a byproduct. But you have a political buy-in in the developing countries that is of a totally different nature. And I think what is happening in China verifies that hypothesis. And I would hope that we could see a lot more of activity along those lines. So let me sum up sort of my way of looking at the world and the role of renewables there. the world is changing very rapidly. We need transformative changes in the energy systems. There's a window of opportunity, because if we miss it, we will have problems with planetary boundaries. We will build a lot of power stations and other systems that have lifetimes of many decades, and we don't have that time. And that goes also on the efficiency side, where buildings constructed will not be changed in a major fashion for 50 years. But we know we have resources and technologies sufficiently. Energy efficiency is priority number one for sustainability, and renewables is the second priority, and it's only together that they can achieve a solution that meets all of the concerns. Electricity will become more and more important. It helps with efficiency. It's a way for renewables to come into the system in an efficient manner. But the really critical issue is to have the policies and have the institutions that make this possible in all countries, internationally, and that adapt situations in these respects to the local needs and conditions. And as I mentioned, energy subsidies and R&D are totally misallocated, and we need a capacity development worldwide. Capacity development has always been argued being a major part of development cooperation with developing countries, and it is and it remains a major concern. But we also realize that we need a lot of development, capacity development, also in the OECD countries. So that's a global concern that really is there, and without which we will not see much of development. Thank you.